Okay, so we'll go ahead and start. If people are still working on the quiz, we'll give you a few more minutes, but we'll begin. Just a reminder, some of the GCC calendar things we talked about last class. Today is a Monday schedule. Tonight is a Friday, so if you have a Friday night class, you go to it. This coming Monday is Patriots Day. There are no day classes scheduled for this coming Monday, but if you have a Monday night class, you go to it this coming Monday, okay? Today, we're going to keep talking about zeros of polynomials, more stuff with polynomials in this thing called long division. I've highlighted the next few classes just to show you where we are in terms of our third test. So we have 4 more days of new material before the test, then we have our review day, and then the test finally is on April 27th, okay? So later this month, it'll be here before you know it, is our third and final test. And so if we go to page 34, we'll just kind of refresh our memories of what we ended with last class. We were looking at this polynomial up here at the top. It's our favorite polynomial. We've seen it a bunch of times. That one right there. And the first question we asked was, what are the values of x that make p of x equal to 0? What value of x makes this thing equal to 0? 2, right? X equals 2. What value of x makes that thing equal to 0? -7. You can just list them when it's factored like that. Part B said find the zeros of the polynomial. Well, that's the same question. It's still asking you for values of x that make the whole thing equal to 0. And for example, x equals -7 makes the whole thing equal to 0. So we ended up with the same answer for A and B. Then we got to part C. It said list the x-intercepts. So the x-intercepts, what did we notice? They were the same numbers as we saw up above. Here is x equals 10. Over there is x equals -7. So finding the zeros is the same as finding the x-intercepts. And then in terms of the factors, for example, you can see x minus 10 is a factor. What value of x does that go hand in hand with? Out of these purple numbers right here, which one corresponded to the x minus 10? Was the positive 10. Which one corresponds to x plus 3? Was the -3. So we had this kind of funny thing where whatever the 0 of thing was, you'd have to change the sign and do x minus that when you put it over in the polynomial, okay? And that was this last guy down here where we talked about x minus whatever numbers you found. That's how we factor the thing. Okay, so let's go to the next page. And we'll try to motivate a little bit of what we're doing with number 5, and then we'll move on. So 5, we can start with Tyler. What is that called in business? It's break even. You guys have heard of the break even point? It's a place where you have where your profit is exactly 0, which isn't the worst thing in the world. What would be worse than having a profit of 0? Having a negative profit. And so business owners are certainly interested in that break-even point. So figuring out where something equals 0 is important to them. In calculus, it comes up all the time. So that is to say, finding where a polynomial equals 0 is the goal of today. It's got, like there are real world reasons to do that. We're not going to see them today. We're just like focusing on the hardcore algebra. Let's find the places where the polynomial equals 0. But hopefully that's a little bit of motivation there. And then to kind of tie it in to the theorem that we saw last class, that thing is really annoying to me because I try to move it out of the way and it just zips back up there. Okay, so the thing that we saw on this previous page, which we're not on. Okay, where are we now? It's Friday, right? Yep. Okay, so the point is that if the polynomial is factored, then it's really easy to pick off the zeros. If the polynomial is factored, it's very easy to pick off the zeros. If the polynomial is not factored, x cubed minus 4x squared plus 5x minus 2, equals 0. Is that easy to solve? Not to me, but if we could factor it, it's easy to solve. All right, so the goal of today is to take a polynomial, write it in factored form, then you can grab the zeros real easy. Actually, no zeros at all will come up. The factors are going to turn out to have i's in them, those imaginary numbers. So, yeah, what did it say? Yeah, maybe the factoring had i's in it if it did. Okay. All right, so we'll see all those today. Let's try number 6. We're going to Katrina. Go ahead. Okay, so each of these guys comes with like strengths and weaknesses. You can use the quadratic formula. It's wonderful, but only if the thing you're looking at is a quadratic. Okay. You can graph and use the 0 command. We've done that before, but the answers will only be approximate. We have high standards in this class. You can factor, but it's really hard to factor. Like factoring something higher than an x squared thing, it's difficult. So that's what we're after today, is somehow come up with a way to find zeros given those 3 different options there. Let's try parts number 7, Brian. Okay. Factor if we're lucky. Do you feel lucky? I don't think that one factors. So if it doesn't factor, what should we use? Quadratic formula. Super, right? Use the quadratic formula. I'm not going to do it, but we could solve that equation. What about finding the zeros in the next example? X cubed minus x squared minus 24x plus 48 equals 0. Can you use the quadratic formula? No. What do you think you might be interested in? Maybe we can graph it. We'll end up doing that. But if there's a quadratic formula, then maybe there's a what? What's the name for a degree 3 thing? Cubic. Maybe there's a cubic formula. Turns out there is. There it is. You know the quadratic formula, negative b plus minus all that stuff. There is the analog. There's a good reason you have never seen it. There's a good reason nobody has asked you to memorize it, because it's that. We draw the line at the quadratic formula. So if you're willing to use this, then all of a sudden, solving this equation becomes a simple matter of plugging into a very big formula, but it's just plugging in. We're not going to go that route. Let's try number 9. We'll go to Michael. Okay, so let's take out the calculators again. And if we have all the quizzes, maybe this is a good time for me to put up the answers. Okay, we have all the quizzes, yes? Yes. That's true, you missed it, I'm sorry. You can talk to me right after class. Okay. All right, so here are my tentative answers to the quiz. Does that look familiar? Can you read that in the back? 5x plus 2 squared minus 5. Oh, plus 5. Wait, did I get them both wrong? I think I did. Negative there, plus 5. We'll just edit that out on the video. Is that right? Is that okay now? Great. It's Friday, right? All right, here's what I got for my my quadratic regression thing. Okay, and I'll take either of those answers, 754 or 753. If you use the rounded coefficients up here, then you get 752.8, I think. If you use the thing in the calculator instead of retyping the rounded version, you get the more accurate answer, which is this guy. Okay, so I would strongly prefer we not retype, but I'll take either answer here. And then over here, degree of this guy was 8. The leading coefficient was -5. End behavior, minus infinity for both, even, and a negative leading coefficient. And then finally, number of extrema could be one less than the degree. That was degree 8. You might have 7 extrema, 7 turning points. Okay, so let's come back here. All right, so what we are doing is we are graphing this polynomial that Michael just read to us right here. So we're going into y equals. And we're going to type that thing in. And once you've typed that in, maybe zoom 6. I think the standard window will be okay for this one. So here's the graph on the standard window. It's not ideal. You can see there's interesting stuff happening that's off of the graph, but that actually doesn't concern me for what we're trying to accomplish here. What we're after are the zeros of the function. How do zeros appear on the graph? As x-intercepts. How many x-intercepts do you see? 3, which makes sense because the degree was 3, and oftentimes those are the same number. Okay, just counting hash marks. 1, 2, 3, 4, 5. Looks like one answer is like negative 5.4. I don't know. Going to the other side. 1, 2, 2.2. Do we see it? What's that biggest one look like it might be? Looks like it might be perfect. Looks like it might be right there on the hash mark that says 4. Okay? So here's our guess. Our guess is that the x-intercept is something around 4, 0. How can we check? Well, if it's supposed to work, then how much should P of 4 equal? Well, it should equal 0. Well, I can do P of 4 right here. I could do it on the main screen if I don't feel like doing the calculations by hand. But I can come out here and I can do 4 cubed minus 4 squared minus 24 times 4 plus the 48. What are we hoping for? We're hoping for 0, if it's perfect. What do you know? Okay, so we looked at it. There's kind of a miracle that happens because we had to use this really fancy tool and guess that one of the nice answers was 4, but then at least we could check and make sure that it really is 4 instead of being like 3.99, which it could have been. Again, there's always an easier way than retyping stuff. If it's already there in y equals, and you're looking at the picture, if you just ask it, if you hit trace and then type in 4, oopsies, let's try this again. If we choose value, which is inside of the calc menu, and then it says how much is x, and we say 4, then it says 0. So there are better ways if you've already got the picture. We've seen some of that before. Okay, we'll go to 10. Andy. Okay, which command were we looking for on the calculator that would tell us was 0? The same 0 that we've been using these same word we've been using these last few classes. So that goes into blank. We could use the 0 command, but there are some weaknesses. Number one, it's only approximate answers. You'll get some decimal. You'll get really accurate decimals, but they're just decimals. Maybe more important is that we kind of got lucky that the other two x-intercepts were real nice. They're on this window. But do you guys remember how long we had to scroll when we were looking at GeoGebra the other day to try to find what the graph was really doing? Well, isn't it possible that this x-intercept isn't here at -5, but really it's at -5 billion? It's going to take a long time. If you don't know where you're looking, it would take a long time to find it, even using the nice tool that we have here. Okay, so we want something better because of those weaknesses. So let's come down here with this more blank stuff. Since x equals blank is a 0, what number did we just figure out as a 0? 4. We figured out 4 was a 0 by looking at the graph and then checking that P of 4 really was 0. Now we come back to that theorem. If you know that x equals 4 is a 0, then there is a certain thing which must be a factor of the polynomial. It's x minus 4. You guys remember that? X minus whatever number you found. X equals 4 works. It must have come from x minus 4. So what that means in the last line here is that the original polynomial, this big cubic thing which we don't really know how to handle, it is definitely equal to x minus 4 times some stuff. I don't know what the stuff is, but at least it's starting to look like this thing underlined in black. This is the goal. If it looks like that, you can just grab the zeros off of it. We now have one factor. It's x minus 4. I don't know what the rest of it is, but at least we're getting there. So it's x minus 4 times some stuff. So how do we find the stuff? Let's try 11. Sarah. Why is that true? Why is 5 definitely a factor of that number? Because it ends in the 0, right? Zeros and 5s. Okay, can you guys do long division? Do you remember long division? No calculators. I'll get you started. We are doing 5 into 34, 60. Pretty quick. Okay, if you know what you're doing with long division, look to the person to your right, and if they don't, help them. It's real easy to forget. That's a really, really nice way to do division by 5. Okay, raise your hand if you remember long division pretty well. Raise your hand if it's like been too long. All right, so let's make sure we're good. Does 5 go into 3? No, we move on. Does 5 go into 34? Yes, how many times? 6. Then what do we do? Then you do this 6 times this 5 and you put the answer down below. Then we get 30. Then what do we do? And we subtract. And we get 4. And then you bring that 6 down, the next thing, and then you repeat. And the reason I'm doing this silly question, which, when do we do long division? Like 4th grade, or I don't know when we do it, is that we are going to do something just like that, but it's going to have x's in it. So I wanted to kind of tie it to something you know how to do, and then we'll try to give you something you don't know how to do. So let's do 5 into 46 is how many? It's 9. 9 times 5, 45. Subtract 1. 0 comes down. 5 into 10, 2. 10 here. What is that last number called? That's the remainder. Are you surprised the remainder was 0? No, you knew it went in evenly. If you got anything not 0, that would be a problem. So what does that mean? It means 3460 is 5 times something. 5 times what? 692. That's what you figured out, right? What did we just do with the number 3460? We factored it, turned it into multiplication. Multiplication is a good thing. Okay, we'll go to Taylor for 12. Okay, so let's try it here in 13. We're going to take our polynomial we've been dealing with all day, and we're going to divide it by x minus 4. How do I know that x minus 4 is going to go in evenly? It's our theorem. We figured out that x minus 4 is going to go into that. It is a factor. So let's do long division. So first of all, which one goes on the outside? It's the x minus 4 into all this stuff. Okay, first thing we need to do is divide. what was the first division we did up here in this arithmetic problem? 5 into 34. That's what we did, right? Okay, let's come back here. You've got x minus 4 into all this gobbledygook. First of all, the x and the 4 do not get treated equally. So I'm just going to put it out there. We are going to discriminate very badly. I'm putting a heart around x because x is going to get all the love in this problem. Here's what you do. You take the x, you put it into x cubed. How many times does x go into x cubed? Okay, so I heard some different answers. It's really not even clear what that means, x into x cubed, because it's variables. So let's go back up here and be really clear. When we did 5 into 34, what we were really doing was a division. When I say 5 into 34, what's on top? 34. And on the bottom, 5. And 5 went into 34 6 times, and then there was some remainder that we had to deal with, right? So it was a division. It was the 34 inside divided by the 5 outside. That's how it always works. We play the same game over here. Which one goes on top? We're doing x into x cubed. What's on top? It's the x cubed, the thing on the inside, just where the 34 was. What's on the bottom? Is the x. The x is our heart. The x is always going to be on the bottom for this problem. What is it equal to? It is equal to x squared. How many times does x go into x cubed? It goes in x squared times, which is a very strange answer because usually the answer is a number. Here it's something with x's in it. Now that we know it goes in x squared, we got to put that x squared somewhere. Where does it go? It goes up above, just like the 6 went up above. So we're going to put that x squared up above. We'll put it up here. I like to make it so that my powers line up, so I'm putting my x squared over the x squared that was already in the under the division symbol. Okay, what did we do up above? You had the 6. You took the 6, you multiplied it by the 5. Here you're going to take the x squared, multiply it by the x minus 4. So right down here, we are putting the x squared that we got times the x minus 4. What is it equal to? Everybody see that? Somebody we haven't heard from yet today, what's the next step? Subtract. That was the next step before. It still is. We subtract. If you subtract these two things, what happens with the x cubes? They cancel. That is not a coincidence. That is what you made happen. By putting the x squared up above in red, you found exactly the thing that was going to cancel this x cubed. If they don't cancel, you've done something wrong. Okay, so then we subtract, and we get down here, what, negative 5x squared? You're going to question me, Sam? Sam says 3x squared. Eliza says no. It's negative 1 minus 4. I got minus 5. Subtract it. So because it's so easy to make this mistake, I would encourage you to put a big minus sign in parentheses. It's really, really easy to make that mistake. So we try again. That's a negative x squared. That's really a plus 4x squared. What is that? That is 3x squared. You win this round. Okay, that was step 1. We have to bring something down. What comes down? The minus 24x. It's sitting up above, waiting its turn. And then we repeat. Something divided by something. Let's see. The first something is always inside there. So what's the term over there we're interested in? It's the 3x squared. Somebody we haven't heard from who gets love on the bottom? X. Every time x is the thing we are dividing by. The x minus 4 isn't completely left out because the x minus 4 did come in when we got to the green part, right? So the minus 4 isn't ignored, but when it comes to the division, it is ignored. How many times does 3x squared, does x go into 3x squared? It goes in 3x times. That 3x goes upstairs in red. It's added. And we take that 3x and do what with it? Multiply it by the x minus 4. So we'll put that in green down here. 3x, x minus 4. X squared minus 12x. Do you like that 3x squared? Yes, because when you subtract, the x squareds will cancel. If they don't, you did something wrong. Okay, so we subtract, and we get x squareds cancel, minus 36x. I did that wrong. You guys are really on my case today, and it's a Friday too. So what should I have put in? What should I put in before I even did the calculation? Minus parentheses. That's how you avoid that mistake. You are subtracting the whole thing. Negative 24x plus 12x is really a negative 12x. What comes down? Plus 48. And we're doing, it's always addition up there in red, but if one of the answers happens to be a negative, then it becomes a subtraction up there. Okay, what goes on top here in my last division is the negative 12x divided by x, all the love. It's equal to negative 12. Minus 12. Then what? Multiply. Negative 12 times x minus 4. We'll put that down there. Negative 12x. I like that. What's next? Plus 48. I really like that. What happens when we subtract? Again, 0. Everybody goes away. Surprised? No, because we knew that we had found a factor. We knew that x minus 4 was going to go into that thing perfectly, which means this last guy, what is this last thing called? The remainder. You knew it was going to be 0. Joe? Like a 0? Yeah, so you can, I'm not sure what you're asking, but I'll say some stuff and then you can ask again. If you tried to divide by x minus 5, you could do everything, and then down here at the bottom, maybe it turned out to be a 7, and that's still the stopping point. It just wasn't, it didn't go in evenly. It wasn't a factor, which is okay. We did need to know this x minus 4 in order to start the process. How did we get the x minus 4? You guys remember? We graphed it. So you need to use that to start the process. Mm-hmm. Yes, everyone that I give you will have a nice number right there. But even if it didn't, even if it was 4.1, it would make it a little messy, but you could do x minus 4.1. And if it was perfect, you'd get a 0 right down there at the bottom. But all the ones I give you will be integers. Okay, so we did all that. And so what does that mean? What does it mean? It means that this x cubed minus x squared minus 24x plus 48 is exactly equal to the product of two things. If you understand division, if you understand what we accomplished there, you should be able to fill in those two blanks. What goes into those two blanks? What was the factor we started with a while ago? X minus 4. And then we did a whole bunch of work. And what did we discover? That's what we discovered. That x squared plus 3x minus 12. Questions on where any of the pieces go? We have to do a little bit more work. Ben? That's what we're going to do. It says, let's find all the zeros. We still have x equals 4 sitting at us. That's easy. Now I have x squared plus 3x minus 12. I can deal with it. It's a quadratic. We know everything there is to know about quadratics. So you took a cubic, which we can't handle, did a lot of work. I'm not saying long division is easy. Turned it into a quadratic. That's the goal. It says here we're supposed to write p of x in completely factored form. Ben says factor this guy right here. If we can factor it, then we're done. That's the goal.
But we already knew we couldn't factor it because it wasn't numbers for that.
Yeah, so unfortunately it doesn't factor. You can try all the possibilities and it won't work. And I really like what Iris contributed there. If it had factored nicely, then you wouldn't have had a messy number, negative 5 point whatever that thing is. You would have had 3 nice numbers. Okay, so how do you handle this guy? Well, we don't leave it. What we're after is figuring out what makes x squared plus 3x minus 12 equals 0. That equals 0 feels like it's just coming out of no place because it wasn't in the problem until now. But we've already seen that finding the factors, which is what we're after, is the same as making the thing equal to 0. Once you know one, you know the other. And how do we solve this? Quadratic formula. So no calculators at this point. Use the quadratic formula. You're going to write down 2 things with radicals in them. Okay, so we use the quadratic formula. We get those 2 zeros. And in fact, so you don't need to do this. You don't need to do this for this question. But just take a look up here again. One of the numbers, power save. It's Friday. One of the numbers looks like it's about how much? 2 point something, 2.2. The other one, negative 5.5 or 4 or something like that. Well, you know what? Those are the 2 numbers you just found. If I type in one of these guys, negative 3 plus the square root of 57, and then divide that by 2, 2 point something small. If I do the same thing, but change what? What are we changing? Make it subtract, right? Plus or minus. You do subtract, and then divide by 2, negative 5.4-ish. Okay, so we found them, exactly. You could have gotten the calculator to give you these numbers 10 minutes ago, but we found exactly what they were in case we need them. So the last thing here, this problem said write the polynomial in completely factored form. It's going to get messy. Let's see if you can stay with me here. P of x equals, what was the first factor that was the easy one? X minus 4, we had that. We got 2 other factors we have to put in here. My theorem says it's x minus and it's x minus. It's always x minus. Whatever the number is, whatever the x-intercept is, whatever the 0 is. What were the zeros? Those guys, right? Negative 3 plus root 57 over 2. Negative 3 plus root 57 over 2. That's one of them. What was the other? Negative 3 minus root 57 over 2. That's the theorem. If you know your zeros, you do x minus those numbers. Those become the factors. Yeah, you leave it just like that. It goes back to that first example we did last class. Tell me, for example, Michael, what value of x makes, not that one, what value of x makes this thing equal to 0? 2. Now go the other way. If I tell you x equals 2, x minus, it's the opposite. Also notice that we put here in red this x minus. I put x minus in front of both. That -3 doesn't become like a +3 in the other one. You're not changing like one particular piece of the quadratic formula. It's x minus, always, 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 x minus. Okay, so go to 15, and where are we now? Taylor, did you read?
Yeah.
Yes. Can we go to Matt? 15. That. Let's find the zeros by just looking at the equation here. What value of x makes the first parenthesis 0? -3. The next one, 2. The last one, 4. It was easy because it was factored. Let's take a look at the picture. We know that the zeros give you x-intercepts. Do you see an x-intercept at -3? Yeah, right there. Do you see an x-intercept at 2? Yeah, right there. An x-intercept at 4? Yeah, right there. But they behave differently. Those things don't all look the same to me. Yeah, this guy just hits and decides to turn around. This guy decides to just...
It doesn't go straight through, it just kind of...
This guy...
looks like a cube.
Yeah, looks like a cube graph. That's a good way to think of it. And in fact... Yeah, and this cube idea, you see a cube in the formula, right? At x minus 2 cubed. So this guy right here, it looks like it's not quite sure what it wants to do. It slows down, decelerates, as Iris says. Is it going to do this? No, okay, I've decided I'm just going to keep going, but at least I pause while I think about it. Whereas at x equals 4, it just goes right through. So here's what I want to accomplish. It's just looking at these powers to know what makes those behaviors. All right, first thing, if the multiplicity, these guys right here, these powers, are what we're calling the multiplicities. If the multiplicity is odd, then the thing crosses the x-axis. So for example, this was an odd one, and this was an odd one, right? Power of 3, power of 1. What was the x-intercept that corresponded to this? It was x equals 2. Does the thing cross the x-axis at x equals 2? Yes, it was up above, then it's down below. What value of x corresponded to that factor? 4. Does the thing cross the x-axis at 4? Yes, it does. Even multiplicities, the graph touches, but doesn't cross the x-axis. Here's an even number. It's squared. What value of x is that factor? It's -3, the opposite always. Does it touch but not cross at -3? Yes, it does. Okay, so even ones are going to come in, they're going to bounce and run away. Odd ones are going to go through. The last thing is there is certainly a difference between how we go through at 2 and how we go through at 4. I will tell you that the way to go through at 4, like going straight through, the only way to go straight through is if you have a power of 1 up there. The only way the thing is just going to go straight through like it doesn't care is if it is to the first power. Yeah, it's like a linear thing. But if it is to anything bigger than 1, for example, 3 or 5 or 7 or 9, it is going to look like this kind of thing where it slows down, ready to turn around, but I'm odd. I will keep going through. Matt.
What if it likes
Yeah, it's a good question. It kind of looks like this guy is riding x equals 2 for a little while, right? Like maybe it's right on the x-axis for like a ½ inch or something. Turns out it's not. If you were to do this on GeoGebra and just zoom in, you would see it pulling away from the x-axis, and it only touches at that one point, although it's close to the x-axis at a lot of points. Okay, so the last thing I think we said was this part right here. If the multiplicity is greater than 1, anything other than 1, it is flat. I would say that this is flat and turns, this is flat and continues on. Let's take a look at 16. I'm giving you a picture right there. Can you write down a formula, a function, that might correspond to that picture? All right, so what are the x-intercepts here? -2, and 2, and also 0. Don't miss the one at the origin there.
Yes, we've got x, x equals 2, and x is 2.
You're way ahead of me. Here's how I start mine. Same as we had before, x minus, every time. I don't care what the number is. If it's a 0, it's x minus. Now we'll put them in. There are zeros. -2. What's the next one? 2, 0. The order doesn't matter, but it's always x minus. Right. Now let's work on the powers. What's happening at x equals -2? It's odd, right? You see that it goes through. That makes it odd. You see that it's flat. That makes it not what number?
Not 1.
Not 1. You put any odd number, odd and greater than 1, I'll give you full credit for it. You can put a 3, you can put a 5, you can put a 19. Anything odd, bigger than 1. X minus 2 it goes hand in hand with which x-intercept? +2. At +2, what kind of a number what kind of a power? It's going to be something even because it turns around, right? You can put a 2, you can put a 4, you can put a 78, any even number up there. And then finally at x equals 0, which is the last guy, what power will make it do that? 1 and only 1, because it shoots right through. It doesn't even pause. It doesn't notice that it's gone through the x-axis. You better put a 1 up there. Matt. Multiplicities are always positive. Yeah, if you put a negative up here, it's not even a polynomial anymore, and that's all that we're talking about. Good question. Okay, so last thing. So we've got our answer up here. Of course, there's freedom because we could have picked different powers, but let me just type this guy in real quick. So somebody read that to me. F of x equals x minus -2 to the third. That is the x plus 2. X minus 2 to the second. Is that right? And then x minus 0 to the first. Oh, 61st. What's... Okay. Is that right? Okay, how does that look?
It's too tall.
It's pretty tall, isn't it? Let's see if we can... Okay, does that look like the picture? Okay. But you can see, yeah, you can see the scale is quite a bit different, right? This guy is on like some nice little window. Looks like the top up here is 1 and maybe 2.7. Just eyeballing it. The top here, 1, I don't know, like 28 or something.
It still has a factor that's
Yeah.
0.
All right, so here's what we need to do.
Vertically compress it.
Here's what we need to do. We need to make this thing not as tall. And so you can see actually that we have a little more freedom than we're giving ourselves. You see in the front of this one, there's a 0.01, which we ignored. But what does that do? It smushes it down. You can put any number you want right in front of this thing, any number at all. All it will do is stretch or compress vertically, but it won't have any impact on the x-intercepts. They'll still look the same. So here's what you're going to do. You're going to ballpark, just ballpark, some point on the graph that I gave you. If you want to estimate this as a 1 and a 2.7, fine. If you want to estimate this point down here, what does that look like? Maybe -1, -1. I would personally grab that because it seems like it's nicer than the other one. But you need to grab some point on there that we haven't looked at. Don't grab one of the x-intercepts. You've gotten all the info you can out of them. But grab another point. For example, -1, -1. And then give yourself the freedom to know that in the front can be any number you want. We'll just call it A. And now what we're going to do is pick the value of A that makes the thing hit the point -1, -1. So instead of the left-hand side, what are we putting for the Y value? -1. that's the second negative 1, equals some a, which I don't know, times how much is x at that point? Negative 1. So I got negative 1 plus 2 cubed, negative 1 minus 2 squared, negative 1 minus 0 to the first. And then there's a little arithmetic to do. So I got a negative 9a on the right-hand side when I did everything out. And then we divide both sides by negative 9. And how much is a? 1/9. Which is a pretty small number, which is, I think, what we want. As Ira said, we're trying to vertically compress this. It was just way too tall. So then as a final formula, I won't write it, but I'll ask you to. Just take that 1/9 and put it, just rewrite that formula with a 1/9 right in the front. What am I about to do on GeoGebra? I'm going to put that 1/9 right in the front of this thing. 1 divided by 9. Okay. How does that look compared to the picture on the paper? It looks pretty good. At what point does it definitely go through this one? This goes through the point negative 1, negative 1. I can plot that point, negative 1 comma negative 1. And you see it right there on the graph. That is what you did by picking 1/9. Pick a different a, it'll look a little different, but the zeros will be exactly the same. Questions on that? Okay, so what I would like for you guys to do, there is a group thing at the bottom of this page, 37. There's not enough time to do all of it right now, so I'm going to ask you to spend your time with part C. Try the other parts over the weekend. We have a long weekend coming up. Maybe there's a little more time for you to practice this. But for the rest of today, let's see how much progress we can make on part C.